Welcome to this unit, and in particular we'll be looking at an introduction of this particular session, and we'll be looking at continuous control systems and a little bit about digital control systems as well. So let's begin. All right, so what's the general definition of a control system? Well, as you might imagine, just like anything, there are a range of different definitions, some more technical than the others, and some everyday ones as well. But I've just chosen a few just to give you a broad overview of the types of things that we see. And sometimes it also shows the validity of the actual source as well. So there are a range of definitions, some are descriptive, others are useful. So in other words, some are descriptive, but then some are quite technical as well. So a control system consists of subsystems and processes, or what are called plants, assembled for the purpose of obtaining a desired output with desired performance given a specific input. So that's basically from that text. A control system is a device or set of devices to manage, command, direct, or regulate the behavior of other devices or systems. And again, that's a pretty broad definition. As you can see, it comes from Wikipedia. Keep in mind that Wikipedia really is not seen as a valid reference source, but I put it in there just to show that sometimes I would highly recommend that you don't use Wikipedia at all for any referencing, but the point of the matter is it's just to highlight to you that some definitions are, you can trust more than others. Also, a control system consists of a combination of components, electrical, mechanical, thermal, or hydraulic, that act together to maintain actual system performance close to a desired set of performance specifications. And this is from the Columbia Electronic Encyclopedia. So as you might imagine, it's kind of like an important society or an important source, so you can give more validity to that. What are some of the advantages of control systems? Well, in a general sense, there are obviously a wide variety of advantages. It depends on the type of control system that you're talking about and also what you're using it for. So these advantages include such things as efficiency, precision, speed, repeatability, amplification, reduction in size and weight of the actual components, the remote control, so you don't have to be there at the particular site, or the plant that you're working at, the input format, the safety recovery time, and the disturbance compensation. So all very, very important characteristics. Some will be taken care of and others will not be able to be taken care of. So some systems will be less stable than others. Some systems will take a longer recovery time. But that's a good set of parameters to use as the basis of discussing the advantages of control systems. The two basic types of control systems that we talk about are open and closed control systems. So we talk about an open loop or a feed-forward control system. So as you can see, you have some desired output response, goes into the control of the black box, some process occurs, and then you get some output that might control temperature or speed of a conveyor belt or something like that. In an open loop control system, you have a cause and effect relationship. So each component is represented by a block which possesses some input or cause, and therefore then inside the black box is some sort of program that wants the system to do something. So you have an effect that occurs, so that comes out of the output, say raise the temperature or perhaps increase the velocity or slow down your conveyor belt, for argument's sake. Now this system can be very sensitive to changes in the processes and external disturbance and simple design. So while it's a particular process, it's not necessarily the best process for all situations. Whereas a closed loop or a feedback control system, as the name implies, therefore what happens is that you get an output and that output gets fed back in and gets compared, so some sort of comparison goes on. So therefore then are you tracking, are you basically following the particular variables that you've set? Do you want it set at a particular temperature, or do you want, as I say, the speed of the conveyor belt, for argument's sake? So that enables you to have a feedback process to see that what you've asked the system to do through your control system, that it's occurring. If it doesn't occur, well, you can, because of that comparison, change the system to be doing what you want it to do. So compared to an open loop control system, a closed loop control system uses a proportion of its actual output to compare the actual output as well with the desired output response. It's commonly known as feedback, and then as we see, it's generally more robust because you're able to feedback information, therefore then make adjustments as you go along, rather than wait for something to happen and then it gets hotter and hotter and hotter, and then you have to basically hit a kill switch on an open loop control system. Now, in this case here with the feedback, it's able to be seen that it's not sensitive to changes as much as the open loop control systems, and it requires rigorous design to avoid instability. And we'll talk more about stability and instability as we move through the different units. So what are the effects of control systems? Well, as you might imagine, feedback system can enable stability. The idea is to bring a system back so that it is stable, or the point of the matter is that you want the machine to be operating at a particular stable level or a particular level, so therefore it's able to do that as well. Gain in bandwidth, well, the effect of these depends upon the design of the control system, and we'll talk more about that in depth at a later time. The sensitivity, well, the feedback reduces the sensitivity to parameter variation and external disturbances. And again, we'll elaborate on all of these as we go through at different topics. The gain, the ratio of the output to the input, is defined as the gain, and it's used to describe that amplification of the steady state of the magnitude of your inputs. The bandwidth, well, that's a natural specification for the system performance in terms of its frequency response, and it's dependent upon the maximum frequency at which the output of a system will track an input sinusoid signal in a satisfactory manner. It's the frequency at which the magnitude frequency response is about -3 dB, decibels, -3 decibels below the magnitude at zero frequency. So again, that's a very formal definition. Once we get into design and analysis at later stages, all of these things will become usable quantities and beyond those basic definitions. But it's a good idea at this stage to know those basic definitions. So the key factor is that when dealing with analysis and design, we appreciate that analysis is the process by which a system's performance is determined, and design is the process which by a system's performance is created or changed. So the major objectives of the system analysis and design is to produce that desired transient response, or natural response, which is the response of a system to a change from its equilibrium conditions. Indeed, any sudden change in a signal is regarded as transient, and therefore transients in an input signal disturb the steady state. Now consider what occurs when the output of a 5-volt direct current or DC power supply is switched on. So you switch it on, the transient response is defined as being from the time that you switch on the particular device and the output reaches a constant 5 volts. Now once this occurs, the power supply reaches what's called its steady state, which is a constant voltage supply of 5 volts. Note that the transient response is not necessarily tied to the on and off events, but at any event that affects the equilibrium of the system. So, you might get a spike in the voltage supply, for argument's sake, so therefore then that's a disturbance. That may, again, trigger a response, which may trigger a fuse, for argument's sake, or the system may be able to handle, a range of particular voltage values or current values, so therefore then the system is able to deal with that. So, they're the other things that the transient response can be affected by. If we're dealing with an RC circuit or resistor capacitor circuit, then the resistor or capacitor is placed with a variable resistor or a variable capacitor for that matter, or you can have both a variable resistor and a variable capacitor, and then the transient response is the response to the change of that resistor or capacitor or resistor and capacitor. Now, if we reduce the steady state response in particular, you end up with what's called a steady state error. So that's just the difference between your expected value, your steady state, and where the system is shifting around. The steady state is an equilibrium condition of an electric circuit or network, which arises as the effects of the transients are no longer important. Now, in designing a control system, it's important how accurately the system performs to the desired response. Particularly, obviously that's what the whole point of designing it to do. So you want to make sure that it matches or aligns itself as close as possible to the design parameters that you've set into it. So if it's desired for the variable under control to take on a particular value, 5 volts, and suddenly something like a spike occurs and you're getting a higher current and a higher voltage through the system and it ends up being, say, 7 volts, well then that's not the desired state that you want. So therefore, then you can have some damage done to the circuit. If not, you have a protective device like a fuse, which would basically protect the device so it doesn't get damaged. Indeed, it would be advantageous to measure how accurately the particular variable can be controlled. So this is you map the steady state error to see how far it is basically swinging off your particular design feature. So you can achieve stability, Control systems must be designed to be stable, because obviously you don't want your conveyor belt going faster than well, safe, and you don't want coal or iron ore flying off the conveyor belt. And obviously you want it moving fast enough that it's efficiently operating and getting the particular product, the coal or the iron ore, to to where you want it to go. So if a system is unstable, then it has the potential to destroy the device, or to render it unsafe at least to operate. So therefore then, stability is a major concern when you're designing. Now, systems that do not achieve stability, if you have that kind of situation, it's impossible obviously to discuss the transient and steady state responses, as they just basically fundamentally require stability to be occurring. Otherwise, that you can't even try to get to a steady state situation, or get the thing to operate at its transient response. In general, a system which remains in a constant state unless affected by some external action, voltage spike, a break in a conveyor belt, that type of thing, then it will return to its constant state when the external action is removed. Well, obviously a trip switch might be in place long before that, because as I say, with a conveyor belt, if you got a tear in the conveyor belt, the system would shut down. So therefore, then you've got an overriding system. Otherwise, you might find that there might be the conveyor belt again, there might be something wrong with the rollers, but there might be a roller that just jars briefly, but that's okay. So therefore, the system has a bit of a jolt through it. But because of vibrations, for argument's sake, the roller might just continue on. So therefore, you go back to steady state and the belt continues on at its proper speed, etc. So for a linear system, the system's total response is what's called a transient or natural response, plus the forced response, which might be, as I say, that roller in the conveyor belt or a spike or something like that. Now, for the system to be useful, the transient or natural response must either eventually approach a value of 0, leaving only the forced response, or it will oscillate. Now, if the transient or natural response grows without bound, in other words, just gets bigger and bigger, rather than diminishes to 0, or it oscillates, so therefore the system becomes uncontrollable, then the transient response is much greater than the forced response, and the system is out of control. That is, the system is unstable or exhibits instability. So you have mechanisms to try and bring it back to stability. Now, number 4, take into account the range of important consideration, such as, the hardware selection. Sure, you can buy stuff off the shelf, you might have to make it in-house, but the reality will be is that how reliable is that system? Where have you brought it from? Is it reliable, a reputable company? Different companies produce different components, whether they are minor components from capacitors to resistors through to pumps, etc., etc. So the point of the matter is that, have you chosen, the best price, the best quality? Now, in real life, obviously that doesn't always occur. You've got, you've got budgets you've got to stay to. You've got a manager that says, no, we need this thing straight away. I don't care. You can spend as much money on it to get that, get that pump so we can pump the water out of the mine, or, get a control system that will enable us to continuously monitor the temperature or the pump pressure, etc., etc. And other times you'll need to obviously realize that it's very important to choose the best you can with what you got. So there's economic impact or cost. So the point there, of course, is that, as I mentioned, that budget allocation, or the other situation too is that with global prices, we live in an international world, so you have competitive pricing. So you might be monitoring prices in America compared to prices in China, compared to prices in Europe or Australia. So you might find that for the delivery cost, it would be cheaper for you to get a comparable component or product from, say, America compared to getting it from Europe. And obviously, robust design is very important. So the system is not sensitive to major parameter changes. You want the system to be able to be robust, meaning that it's able to, a little bit of hiccup, small changes in current, voltage, temperature, etc., etc. It's able to work within some design parameters. Now, overall, the design process, basically, as you might imagine, it's an orderly sequence for the design of the feedback control systems. First thing is to transform your requirements into a physical system. So draw a functional diagram, and we'll talk more about that. The functional block diagrams have, if you like, their own language, and we'll see that different shapes mean different things, and also we'll talk about cascading block diagrams and that type of thing. So that language and use of those type of terminology will become evident as we move forward as well. create a schematic. In other words, how does it all fit together? How does it interact? What are the key values in terms of voltage or capacitance, resistance, all that type of thing? Develop a mathematical model. Again, your block diagram helps you with that. So the mathematical process is very important because you're using it to simulate or emulate the process. So you need to be able to design it such that, you know, your mathematics is modeling the behavior as close as possible to the actual processes that are occurring. So you might have to use differential equations, and we'll see that as we go through, or you might have to use fuzzy logic or something like that. It depends on how complicated things are. Then you reduce the block diagram, because the point of the matter is that you've got this tension between simplicity, efficiency, and what you're trying to do is to make sure that you don't have, well, repeatability where it's not necessary, or redundancies where it's not necessary. Redundancies are important, but again, if you can reduce that block diagram so that it operates appropriately with some inbuilt redundancy, for argument's sake, and some other safety features, then that's the way to go. Then you need to analyze and design using your standard test input. So you've got this device, you've gone from concept to basically building a model, for argument's sake, doing a little test site. So you're going to put some data into it. So you might have to either generate some data, or you might, from your process, be able to put that data through the system. So you want to test it for different impulses. Typically what we do is we use step, ramp, parabolic and sinusoidal signals. But it depends on what your application for it is. So your input may well just be sinusoidal, for argument's sake. But it'll depend on your system. So what we're saying is that whatever your control system is being used for, you would test it for your specific inputs and values, just to test that you are getting out the data or the outputs that you would, you'd be expecting. So if we concentrate on the mathematical modeling part, then we're going to start by modeling what's called the frequency domain. So these mathematical models are transfer functions, what we call transfer functions in the frequency domain. The state equations are in the time domain. So to develop a mathematical model, you'll need to draw on all your fundamental knowledge of mathematics and also physical principles. So things like Kirchhoff's voltage laws, Kirchhoff's current laws, flow rates, pressure laws, Newton's laws, all those kind of fundamental principles that you'll have to bring to bear on your particular system. So a differential equation can be described by inputs and outputs. That's our typical form. That's a general nth order linear time invariant differential equation. So you do a lot with differential equations. Now the system parameters, or the coefficients and the outputs, that's CT. If you have a look at that. So CT and also R of T, you'll find that that's your input. So what you're seeing is here's all your inputs on this side. Things change on these inputs, and therefore that's going to give you a change in your output. So you're monitoring, trying to get a desired output by changing your inputs. Okay, so therefore then it's that's why we have an equal sign here, because you're trying to make sure that whatever occurs on this side of the equation, ultimately the effect of each of those individual things will add up to give you the desired output that you want. Now we have a preference for inputs and outputs and systems which are distinct and separate subsystems, and we can define those as transfer functions. Why? Because they are easy to contemplate and manipulate. So in other words, we start looking at some of our mathematical modeling by trying to model as much as possible, because it's only an analogy. It's as best as we can get. The real system may operate slightly differently because there might be other variables we're not aware of, or other variables that become more important at different times. So that's all we can do. We can just model as best we can, and then tinker with it to refine our model. We can show that the range of variation of S, or the domain of S, schematically as a plane with a horizontal axis of this plane, the real axis, since this is defined as S equals sigma plus J0. So in other words, there's no J or imaginary part. So therefore then it is S equals sigma, which is our real part. The vertical axis is known as the imaginary axis and is represented by S equals 0 plus J omega, or S equals J omega. So what we're saying is that along that axis, things are imaginary in number form. The origin is represented by the complex zeros. In other words, that S equals 0, real number across the axis, and you go up 0 on the imaginary axis. So S equals 0 at that crossover point. So that's your crossover of your two axes. So we consider our S-plane. We're just basically now drawing a little diagram. So when you do that, as you can see, we've got the imaginary axis, the vertical axis, and the real axis is the x-axis. So the left half plane and the right half plane. Now they become quite significant when we start talking about stability and other parts of the process. So the left half plane is the region, surprise, surprise, left of the imaginary axis. So everything from negative infinity all the way through to 0 on the left-hand side of our imaginary axis. And as you might imagine, the right half plane is the region right of the imaginary axis, or everything from 0 through to infinity on the right-hand side. So the whole complex plane is called the S-plane, and S equals sigma plus j omega, and we say that we're operating in the frequency domain. How can we transfer between the frequency plane and the time domain? Well, we use things like Laplace transform as one particular process. So we're going to recap on how you go about using the Laplace transform to do those types of things. So the difference equation defined above, or the difference equation, is difficult to model or represent as a block diagram. So the Laplace transform enables us to define inputs, outputs, and the system as separate entities and define the relationships simply and algebraically. Laplace transform is that integral value, as you can see there, and basically there's a whole set of tables that you look up, and we'll see as we do some examples how we go about doing that. Nothing new to you, you've done Laplace transforms before, so it should be any big surprise to you. Sigma is our real part, and omega is the imaginary part of S. F of S is the Laplace transform of f of t, so that's the time domain. This is the frequency domain, this is the time domain. So what we can do is convert from the time domain into the frequency domain using the Laplace transform, and then we can also use the inverse Laplace transform to go from the frequency domain into the time domain. So technically that's what we're doing in terms of an integral. So don't get bogged down in the mathematics, but we'll just do a bit of a recap on the background of the mathematics. So the Laplace transform converts differential equations into linear equations, which can be manipulated algebraically to give a transfer function. Consequently, the Laplace transform takes the time signal, f of t, which is a function of t, and integrates out the time variable to produce a function x of s of the complex variable s, which is the frequency domain, as we know that s equals sigma plus j omega. So then what you do is you have this whole range of different transfer functions so that you can fit those and transfer between the time domain and, as you saw, the frequency domain. Now, that's only a limited number there from your textbook, but you should be able to, you know, on the internet, find a whole range of values. So there are many values. So it just depends on which particular system, which particular differential equation you're working with, you'll need to go and find those particular values. Then you have a whole range of theorems that you're able to use. And again, this is the basic ones. So the Laplace transform process is a tool that provides algebraic simplicity. So you're going from those complicated differential equations into linear equations. It allows important presentation of process by input and output relationships. It enables a transfer from complex to simplified descriptions that you're able to work in, and then when you're finished, you're able to transfer them back into the complex system using the inverse Laplace transform. Now, there are different processes that you can use. The typical one is partial fraction expansion. Again, this should be nothing new to you, it's just a mathematical process. So to find that inverse Laplace transform of such a complicated looking function, it's possible to convert that function into, break it up into a sum of simpler terms. However, that conversion into those simpler terms is the process that we call the partial fraction separation, if you like. Now, you must first of all ensure you've got a proper fraction, because otherwise it doesn't work. So the first thing you have to do when you're going to do your partial fraction breakdown is to ensure that the degree of the numerator, which we can call p of x, and compare that to the degree of the denominator, q of x. Now, if the degree of p of x, in other words, you know, have you got x squared, x cubes? So if the degree of that numerator is higher than the degree of the denominator, then you need to divide through. So you need to use basic division. And if you do that, because that particular situation where p of x is higher than the degree of q of x, then it's not a proper fraction. Mathematically, it's called a proper fraction. So you'll need to use that polynomial division to produce and precede that. So let's try an example. So here we have f of s equals 2 divided by s plus 1, s plus 2 as factors on the denominator. Now, sometimes they're already multiplied out. You might have to factorize it. So that's quadratic if you multiply that, of course. So sometimes you have to simplify it. Sometimes you have to expand it. It just depends on the particular process. So if you're given the expression in terms of s squared plus blah, blah, you would need to go and factorize it. That helps greatly when you go about doing your process with regards to the partial fractions. So here, the first thing you have to do is ensure that you've got a proper fraction. So as we said beforehand, we've got to make sure that the degree of the numerator, p of x, is lower than the degree of q of x, the function in the denominator. So as you can see here on the top, we've got s to the 0, if you like, because we've just got 2. So the highest power of a variable s is s to the 0, because s to the 0 equals 1. And then on the bottom, if we multiply that out, that would be an s squared would be the highest power. So therefore, then we do have a proper fraction. So we don't have to do anything, no polynomial division, thank God. So we can just move straight on. So when we do that, there are 2 ways you can go about doing a partial fraction. I'm going to show you both methods. You can choose whichever method you feel comfortable with, whatever works for you. So when you do the expansion, you've got to be careful. There are little rules to do with that. But here, we're going to take f of s equals 2 divided by s plus 1, multiplied by the other factor s plus 2. So we can separate those into k1 over s plus 1 plus k2 over s plus 2. So what we want to do is to form a common denominator. So if we look at that carefully, we can multiply through by s plus 1, and we can just get the s plus 2 on the bottom now. Now, when we do that, as you can see, we can do a comparison and just follow your mathematics through there. So we end up with 2 divided by s plus 2 equals k1 plus s plus 1 k2 over s plus 2. So if we look at that and we want to eliminate this and see what happens, these are basic processes like taking limits. So let's see what happens when we let s approach -1. So let's do that. So it gets closer and closer to -1. So we're going to set it to -1. Then it will eliminate this term because that's going to be -1 plus 1. As you can see, -1 plus 1. So that's going to drop that out. So it becomes a 0 term. So what that enables us to do is to find one of our unknowns. In this case, we're going to find, by a bit of manipulation, that k1 equals the value 2. We can do exactly the same process again. Let's multiply through by s plus 2. We eliminate the s plus 2 on this side, but remember, whatever you're doing to the left-hand side, you've got to do the right-hand side. So we multiply through by that, and as you can see again, we get a little expression, and we're going to do the limit, and see what happens as s tends to -2. Obviously, as it gets closer to -2, so we set it to -2. And again, as you can see, we're going to drop out this term here. So now we have a value for k2. So really what that tells us is that our k1 value was 2 and our k2 value was -2. So now we have that original function broken down into partial fractions. This enables us now to do things by just concentrating on each of these particular parts of the partial fraction bit by bit. So if we use the Laplace transform table, we'll find that this particular term goes from the frequency domain into the time domain, and that is the general form. When we have that particular form looking up the table, then that will be the form that we have when we do our Laplace transform. Likewise, here for this one, that will be what occurs for the Laplace transform table values as we look it up. So that ultimately now is the Laplace transform has occurred, and then we might either manipulate this, do some analysis with this, but now we're able to have it in a the time domain and operate with particular values from the time domain. We might be tracking data in that way. Likewise here, method 2. So the method 2, exactly the same. We're just going to go through a process to show you can choose either way to do the partial fraction. So here we do obtain a common denominator. Beforehand, we were doing an elimination process basically by multiplying through the factor and getting rid of it. And remember, we've got to make sure that we're consistent in our approach. So to obtain a common denominator, you can see that we want a common denominator which has got the factor s plus 1 multiplied by the factor s plus 2. So To get that, we have to, as you can see, multiply it by s plus 2 over s plus 2, s plus 1 over s plus 1. So as we do that, we can see very, very clearly that just by getting a common denominator, it's a bit complicated, but ultimately you'll get this. So we can compare up here. We can see we've got a common denominator on the right-hand side, a common denominator on the left-hand side. So now, because our two denominators are the same, we can now compare our numerators. And again, it looks complicated, but it's not that complicated. Now, since our numerators are equal, we can equate those coefficients. So here's our s to the 1 term, so we can equate that. Now, we don't have any s to the 1 terms on this side, because this is really 2 times s to the 0, because s to the 0 is 1. So therefore then, that 0 equals k1 plus k2. So therefore, straight away we can say k1 must equal negative k2. And the same thing here with s0. We know that on the left-hand side is equal to 2, so on the right-hand side it just equals this term here for that particular form on the denominator. Now, we can go through, use our two equations, and again, oh, surprise, surprise, we find that k2 equals negative 2, do a bit of back substitution, rearranging, and k1 equals 2. So as you, surprise, surprise, as you might imagine, you're going to end up with exactly the same partial fraction. Actually, no big surprises. So then you can use that, since you now have the partial fractions split up, you now have things that are able to be, transformed using the Laplace transform table. And again, we end up with exactly the same expression in the time domain. The key thing is that you can use either process, whatever suits you. All right. So that was all about analog or digital systems is something that we need to consider as well. So now we move from the analog, which is what we call continuous systems. Continuous systems enable, values 0, 1.333, 1.767, 22.9888. So, but with digital, we know that we have whole numbers. So we can only have, ultimately we'll be dealing with 0 and 1s. So therefore, digital systems enable us to operate with, that type of digital system compared to the continuous. So when we look at digital systems, the advantages of digital computers over the analog systems are that digital computers can reduce costs, have flexibility in response to design changes, and also noise immunity. Now, typically, the computer replaces the cascade compensator and is positioned as followed. So you have a to D, which is a analog to digital converter. You need to be able to communicate with the digital computer in digital signals, so that's why you need your converter. You do whatever you need to do, and then basically take that digital computation response that you've got, convert it back into an analog signal, and then that drives your plan. So it may have to send a signal off to do whatever it needs to do. This is the feedback, so feedback, again, comparison, away we go again. So the digital analog converter is simple, it's effectively instantaneous, and the analog to digital converter is a two-step process, it's not instantaneous. There's a delay between that input analog voltage and output digital word. The analog signal is first converted to a sampled signal, and then it's converted to a sequence of digital signals or binary numbers. The sampling rate needs to be twice the bandwidth of the signal, otherwise distortion occurs. So we have a minimum sampling frequency called a Nyquist frequency. Again, these things will become more important as we go through and look at specific examples and do some design work with them. So sampling, here's your continuous signal. So what you do is with your sampling, you staircase it, and basically what you're trying to do is to have a set of continuous or analog signals that have been converted into, well, it's representative really, to be honest, as you can see. It's not obviously because of the nature of the step process. And then it depends. If you have a large step or sampling, then obviously it won't necessarily map the particular continuous. So the, the step size or the sampling rate or sampling size or time, sampling time is very, very important, because then you get a more representative signal. So you end up with all this digital data. Okay, so we're starting with the analog signal. So there's our analog signal. Basically, I've just gone through all of this. Sample analog signal at a period intervals. Then sampling interval uses a device, what's called a zero order sample and hold, and we'll talk more about that again, it becomes, some of these things, what we don't look is just look at the fundamentals, the theory, and then ultimately get back on to doing examples and utilizing these things. So, you know, if you get a bit tongue twisted with the mathematics, don't worry too much. Just hold in there, pick up some of the terminology, and then the application of it is what's important. So that zero order sample and hold process yields that staircase approximation. So that's what we're doing. So understandably, if higher order holds, there are higher order holds, but we're just going to concentrate on the zero order sample and hold. Other units of higher, you know, level than the introductory unit, we'll deal with those. But it's good to know that they do exist. After sampling and holding, that analog to digital converter converts that analog signal to a digital signal. So consequently, the dynamical range of that analog signal's voltage is divided into two discrete levels. Each level is assigned a digital number. It's quantized. That's the whole idea. Quantized means that you have packets of things compared to continuous, which is you know, a range of things. So yes, so you end up with that digital representation. And obviously that's what talk to the computer, get it to do what it wants to do, and then obviously you need to go back the other way to get it back into an analog signal and operate from it. So modeling the sampler. As we said before, the idea is to represent that digital signal as a sampler and zero order hold. In particular, to represent as a transfer function similar to other subsystems, and in sampling the signals, the Laplace transform becomes unwieldy. So you need to replace it with another transform called the Z transform. So for digitals, we talk about the Z transform. For continuous systems, we talk about the Laplace transform. So again, this is the background mathematics for that. Here's your sampler going through. So modeling the zero order hold. It yields a staircase approximation, which we've seen, to our time function, which represents, results in that zero. We call it zero star because it is only representative, if you remember, because we're sampling of the original continuous signal. So it's mathematically, it's basically approximated by a series of what's called delta functions. And as I said, don't get hung up on the mathematics. Look at the application of the mathematics as we go through the problems and examples. But obviously, we just can't jump into problems. We give you the background and theoretical information as well. Now, this involves the production of a number of step functions with the amplitude of your function in the time domain at the sampling instant of fk of t. Taking the Laplace transform, you end up with this little expression for your hold. This equation demonstrates that the hold circuit integrates the input and holds its value over the sampling interval. All right. As you might imagine, you like the Laplace transforms. For the digital area of control systems, you have Z transforms. The stability and transient response of the analog signal or system is dependent upon gain and component values. In digital systems, sampled data system stability and transient response is dependent upon the sampling rate or the sampling interval or the sampling time. They'll be the type of terms that you'll see. As indicated above, the Laplace transform becomes unwieldy for sampling data systems, and so in order to have a process whereby we're able to get that information from the sampling with as much ease and accuracy, efficiency as we can, we have to move across to the Z transform. So again, you're able to move between the frequency domain and also the time domain as you move through. So again, as we say, for the Z transform, you have inverse transforms, etc. So let's have a look at an example in the digital domain, or the digital area. Now, if our sampling interval, sampling time, sampling rate, they're all the different expressions that we will use, is about 0.1 seconds. Using the partial fraction expansion, determine the Z transform for this particular function. Now, you'll notice it's in terms of frequency domain. It's all in S's, so that's the frequency domain. So there's our particular plant function control system. So therefore, then we go about checking. Now, as soon as we see partial fractions, we have to say to ourselves, is it a proper fraction? So we do a quick test and we see, oh, yes, that's got s to the 0 in the top. And this, if I multiply that, it's going to have x cubed. So straight away, we know that it's a proper fraction because the degree of the polynomial in the numerator is lower than that in the denominator. So we're very, very happy. We don't have to do any polynomial division, so we can move straight on. So the partial fraction, as we see, again, keeping in mind there's little rules to do with how you split this up, so you should go and recap on your mathematics and check that you're doing that correctly. So in this, to take this particular expression here and turn it into a partial fraction, we need to find these values A, B, and C. Now, as I said beforehand, you can use either of those two methods. I'm going to use the one where you get a common denominator here. So we form a common denominator, go through and do that, collect up our terms, and then what we can see is that we've now got the same denominator as before on the left-hand side. So great, so what we want to do is equate all the coefficients on the left-hand side with the coefficients on the right-hand side. So when we do that, we can see that we've got s squared terms. There's no s squared on the left-hand side, so we have this expression. We can start to manipulate it. S1, again, there's no S1 term on the left-hand side, and S0. So now, oh, look, we're able to get a value. And then basically we've got three equations with three unknowns, simultaneous equations. So really, again, some basic mathematics. We go through using simultaneous equations. We're able to find our C value, first of all, do some back substitutions, find our B value, and then consequently we can see that we've got our A, B, and C values. So now our original partial fraction looks like this. Now I'd recommend that you work in decimals and work to 4 decimal places as you go. So that's really 0.2500. The reason why I say work to 4 decimal places is that at least you have a consistent approach. So adopt that straight away and you'll find that you'll be able to compare values as you go through with my particular solutions in the tutorial, etc., etc. But it's just a good rule of thumb. That way you can keep track of things. So you take the Laplace, inverse Laplace transform to begin with. So we're going to get this into a form so that it's in the time domain. So there you go. Then what you're able to do, once you get it in there, just go through individually and do your Laplace transforms. And I've done every mathematical line. So all you do is go look up the table and look for the transforms. And then we have to use the partial Z transform table. So when we do that, we're able to transform those. And remember, we're evaluating for a sampling interval of t equals 0.1 seconds. So again, go through the process. We're doing Z transforms on each of these now. So here's a Z transform of that, a Z transform of this, and a Z transform of that. So what I'm doing here is, again, every mathematical step to make it clear to you. So I've taken out, these are just constant values, so I can take them out the front like I've shown, and then basically you can evaluate the internal value by using your Z transforms. Work through, and then you need to simplify. So always need to simplify, and there's our partial fraction now. So we work through, and then yes, as you can see, we have to consider each of our terms in the numerator. So as we shuffle through, so all I'm doing now is, since this is so big, I'm just doing it in bite sizes, so I'm going to concentrate on this particular term to begin with, expand it out, take this particular, these two factors here, there's my two factors, expand it out, these two factors. What I'm trying to do is to do it so I can simplify overall. That's not the simplest form. The other thing in mathematics and in control systems and all mathematical things when you're designing, you have to get it down to the simplest mathematical form. That is not the simplest mathematical form. That's why we're doing it. So likewise, take these two factors and multiply them through. So then what we do is we have all these individuals, so there's a z cubed, and a z cubed, z squared, z's, etc. So we're able to now put all that together and basically keep simplifying our numerator. So that's what our numerator ultimately looks like. Likewise, our denominator is this factor multiplied by this factor multiplied by that factor. So again, what we're going to do is take that factor, and that factor, multiply it out, and we again end up with something z cubed in that particular expression. So we combine the numerator and denominator just like we did beforehand, and you end up with the total Z transform. So this is in its simplest mathematical form. And again, that's important. You'll see we're working to 4 decimal places like I mentioned. That's something I set. It's just a good way to work for consistency, as I say, and that way good comparison with my values, plus also just gives you a system, a process to follow. So now that's what we've ended up with. We've ended up with our Z transform. So basically, overall, we've started some introductory concepts with regards to control systems, definitions thereof, looking at analog or continuous systems, and looking at digital systems which enable us to do a whole range of analysis and design. All right, take care.